In scientific experiments, it can be hard to know if the result you obtained is the accurate or true value. This is why scientists do their best to identify and minimize any sources of error in the experimental design. In some fields, like biology, sports science, and psychology, dealing with living specimens, especially complex and long-lived ones with diverse lifestyles like people, means there are a lot of factors that cannot be controlled. So large sample sizes are needed to compensate for all these random errors, and calculating the standard deviation may be a useful tool for indicating the spread of the data. When dealing with chemical compounds and physical tests that tend to vary quite little in composition, or in fact may even be repeat measurements using the very same objects or the same chemical solutions, the variance in our data is usually quite minimal, meaning the results are quite precise or close to one another, or we could say that they are very reproducible. And most of the random errors probably come from small differences in how we actually took the measurements. These small differences are called measurement uncertainties. To minimize uncertainties when designing an experiment, it is best to choose equipment with the highest level of precision possible that falls within the scale of what you want to measure. Say you wanted to accurately use 100 centimeters cubed of a solution, you would have a very big uncertainty if you used the approximate line on a beaker, but a much, much smaller uncertainty if you used a finely calibrated volumetric flask. When carrying out your experiment, it is good practice to keep track of the uncertainties of the equipment as you go. If the equipment has an uncertainty value written on it, use it. The 5 milliliter volumetric or bulb pipette on the right has an uncertainty of 0.15 mils. Milliliters are the same as centimeters cubed, by the way, and you may wish to use cubic centimeters since the SI unit for volume is cubic meters. If an instrument doesn't have a reported uncertainty and it happens to be a digital instrument like the electronic or analytic balance as in the image, then look at the smallest decimal place. 1 increment is your uncertainty. So for this one here that goes to 4 decimal places, we would say our uncertainty is plus or minus 0.0001 grams. If you're using an analog instrument, so something that is not digital, that needs to be read by eye, like this measuring or graduated cylinder here, it is fair to say that when you read from the marking, the true value could fall within half an increment above or below what you're seeing. So the graduation of 2 centimeters cubed in this example here means we would say that the uncertainty is plus or minus 1 centimeter cubed. In the burette, the graduations are 0.1 centimeter cubed apart, meaning your uncertainty is plus or minus 0.05. You should estimate when taking a reading so that your measurement is also to 2 decimal places. The word propagation means growing or spreading. Propagating plants means breeding them. Propagating ideas means sharing or promoting your thoughts through a group. Propagating errors is about carrying your uncertainties through. So kind of growing them or spreading them from one calculated value to the next so that you can add them all up and quantify the uncertainty of the final results you calculate in your experiment. Since measurements are taken with different units, this requires you to convert all of the uncertainties to percentages before you can add them together. In an IA, you should have at least 5 data points that you will plot on a graph. Each one will have a different uncertainty value. You need to show a sample calculation for just one of them. In this example, I'll show you a set of data for an experiment where samples of wine have been left open and exposed to air, and the ethanol that has been oxidized to ethanoic acid has been titrated with sodium hydroxide. As well as calculating the uncertainties, it is important to recognize that it is a big assumption that all of the acid present is ethanoic and that it is all derived from the alcohol. So don't forget to include these sorts of comments in your evaluation as well. So let's go now to an Excel spreadsheet. This is going to be a little rough around the edges, and I'm sure there'll be other tweaks that could be made, but hopefully all the big ideas are here. So we start with our burette readings recorded when we were doing the experiment. Notice that in a table of raw data, I include uncertainties as a plus or minus value in the heading. I also just keep the units in the heading and keep them out of the rest of the table. Excel is not very good at reading units. In your report, you can include raw data as a separate table to your processed or calculated data, or you can present it all together if it fits in an easy-to-read table, preferably without going over a page in your document. Here, I will now add the titer volumes by subtracting the final from initial readings. Because the titer volume has an uncertainty of 0.05 for 2 readings, I have to combine them to make an uncertainty of 0.10 for the titer. If you're not familiar with formatting functions in Excel, select the text in the formula bar up the top and click the small toggle at the bottom of the font section to reach the option of superscript. This is what you need to type in something that's an index or power, like here, to make it centimeters cubed. This button merges or joins cells together, and this one stops the text from kind of leaking out the side of the cell, instead making it go onto another line. Now I type a formula. Anything starting with an equal sign is an instruction for Excel to do something. I type equals, click on the cell with the information I want, a hyphen for a minus sign, and the other cell I need. Enter. If I hover my mouse over the bottom right corner of the cell until I see a black cross, I can click and drag to copy the formula down the column, which automatically adjusts to read the correct row of data for the information that's input into the formula. The borders button can help it look more like a real table, or at least to make it easier to follow, or when copying and pasting into Word. In this experiment, the repeat titrations or trials were carried out using aliquots of wine from the same flask. So they should all have the same concentration of ethanoic acid. When I mean that, I mean all of the trials for a single time increment. Notice that one of my results here in the titer volumes that I've calculated, one of my results is outside the range of 0.1 centimeters cubed compared with the others. So don't use that one. Only the concordant data or data within one increment of the uncertainty should be included in the process data in this case. Concordant data is only relevant when you are using the same solutions or same objects for each trial. For other types of investigations, you might have a bigger variation because you're actually taking measurements from different samples. The formula to find the mean is to type equals, the word average, and an open bracket. Then you can click on the cells with the information you're using. If you need to avoid data that's not concordant, like I've color-coded here, you can hold down the control button while single-clicking the mouse on each cell that you need and press enter. These buttons here toggle the number of decimal places displayed. The significant figures in the average values should be consistent with those in the raw data, whichever is the smallest. To show sample calculations, you can do this straight into Word if you prefer, but I'll show you in the spreadsheet where we can see the data and keep formatting my work in tables, as I find this neat and easy to follow without taking up too much space. So let's think of all the things I'll be calculating with my data. I will convert my titer volume into the moles of sodium hydroxide used. This means I can work out how many moles of acid it reacted with. I haven't displayed the equation here, but the stoichiometric ratio is 1 to 1. So moles of sodium hydroxide equals moles of ethanoic acid. Then, knowing how big my aliquot of oxidized wine was, I can turn the moles of ethanoic acid into a concentration by dividing by the volume. Next to the formula for each calculation, include a worked example. It doesn't matter which data point you pick, but use the same one throughout all the workings. To add a formula using Equation Editor, click Insert at the top, and then you'll find Equation with the symbols. Watch out, if you start typing in a cell an equal sign, remember Excel will think you want it to solve a formula. To override this, you can change the cell type to text instead of general, or just use the equation editor again. All right, on to the uncertainties. We can itemize all the measurements we made that contribute to the calculations in the table above. Give an example of a measured value and the percentage the uncertainty has been turned into. So we have the titer volume. Divide the uncertainty by the value you measured. You can multiply this by 100 to make it a percentage, or if you click the percentage button in Excel, it automatically converts the decimal for you. Now, what isn't in the results table, but was part of this process that you didn't see, was making the standard solution of sodium hydroxide. Since the moles of sodium hydroxide are in our calculations above, we need that uncertainty too. So we have the electronic balance we weighed it out on, and the volumetric flask we added water to dissolve the sodium hydroxide and make the titrant solution. The volume of wine used in each titration, or the aliquot, was 20 centimeters cubed, and the uncertainty was written on the volumetric pipette. Most uncertainty values have only one significant figure, and generally by convention that's what we use. But if there are more stated on the equipment, you might as well use them, and be consistent when converting to percentages. Finally, type in equals, sum, open bracket, then click on all your percentages. And this is the total percentage uncertainty. To find the absolute uncertainty, the percentage needs to be multiplied by the final value you calculated, in this case, the ethanoic acid concentration. If you have not used Excel to formulate this as a percentage to format this as a percentage for you, you will need to divide by 100 first. But if Excel recognizes that this is a percentage value, there's no need to do this. So be careful you track everything through properly, or double check your calculations with pen and paper if you need to, so that you're not out by a factor of 100 or maybe 1,000 if you haven't converted your units from centimeters cubed to decimeters cubed. So we multiply the percentage by the 0.0710 moles per decimeter cubed. And our limiting number of significant figures in our uncertainties is 1. So we just keep one significant figure here. Is there an easy way to get Excel to do this for us and add it to our table? Sure. The formula will be a little longer, but now we know what we are looking for. It shouldn't be too hard. Let's just insert some extra columns so we don't run out of space. We'll add in the concentration data and put space for the uncertainty. So the concentration needs a formula. We type equals, click on the titer volume, and multiply by the concentration of the sodium hydroxide. That gets us to our moles in our aliquot. Type a / to mean divided by, and we'll type 20 for the volume of our aliquot. There we go. From the correct rows again. Merge cells and whatnot if you'd like to adjust the look of it. For the uncertainty, we need to start our formula with equals, then 0.10 / and click on where you have the titer volume. When we copy and paste the finished formula, we want it to always read the mean titer from the right spot. So remember, this will adjust automatically when we go down the page. Next, we add the uncertainties for the sodium hydroxide mass, water volume, and wine aliquot volume. These uncertainties, unlike titer, don't change. They're identical for all of our time increments. Since I don't want Excel to auto-adjust my formula when I copy and paste it this time, I'm going to put a $ in the middle before the cell number. This locks the formula to this row. If you want to lock it to a column, you can put the $ before the letter. If you want to lock it to one cell in particular, put a $ in front of the letter and the number. Here, I just have the $ in front of the number, so the row is locked. And I have $ in all three of these values, so they stay the same. I'm also going to put brackets around everything I've got so far after where I've typed the equal sign. And then I will type an asterisk to mean multiply, and I can click on the cell with the ethanoic acid concentration. Phew! Now, most of these are actually pretty similar. I can add more significant figures just to show you that they aren't really the same, but I can't leave them like that because that would be breaking convention. So back to one significant figure, and our uncertainties are actually all very similar. Make some cosmetic touches if you want to. Okay, so you have your data, you have a calculation showing you're working, and you have uncertainties. You can highlight the data now to graph it. Only your averages, with your independent variable on the x-axis and your dependent variable on the y. Some features to add include grid lines to make it easier to interpret data, and you may wish to add error bars to show the uncertainties. Delete the horizontal ones when they appear. For the vertical ones, you will need to go into the options panel and scroll down to custom. Highlight your uncertainty values in your table to put in place the positive and negative values. This means how big the bars are, both above and below the points. If your uncertainty values are in line with the graph data in your table, they will match up automatically. Notice we never included the uncertainty of the exposure time when we were converting to percentages. Why not? Well, time wasn't part of our calculations to get ethanoic acid concentration, so it shouldn't be part of our propagated errors. Instead, the uncertainty for time should just be left as a plus or minus value in the axis title on our graph. Now, I could talk a lot more about graphing here, but I don't want to get carried away. I will make a warning, though, not to get ahead of yourself when trying to add a line of best fit. If you add a trend line in Excel, it's very tempting to look for the graph shape that gives you the highest R-squared value. The R-squared value indicates goodness of fit, which means the equation it generates for you passes closely or through all of your data points. However, 99% of the time, the best fit is a polynomial function because you can make something like a cubic function fit just about anything. It's completely illogical though, because if you were to extrapolate that graph, it would suddenly go in a completely different direction to the true trend in the data. Like here, it's put in a quadratic function, but realistically, a point will be reached where the ethanoic acid concentration stops increasing. And some graph shapes like sigmoid functions aren't possible on Excel, so just watch out. Or be very clear that the apparent equation only describes the data over the range you have tested. Sometimes it's actually just better to try to draw a curve by hand. And don't extend it beyond the points you plotted, and use your scientific mind to discuss the actual nature of the relationship between the variables. The other thing I wanted to make mention of while I'm here is the distinction between a graph like this and one that shows a rate. What you decide to investigate is up to you, but be very careful to make sure that what you show in your graph is an exact match to your research question. If you asked about the rate of oxidation in wine after the bottle has been opened, then you actually need to determine a change in concentration. If you said rate, you need to find the difference in an initial and a concentration at a certain time point and divide it by the time. So you get that rate as a change per hour or per minute or second or whatever unit is suitable. You can't see my starting concentration here, but I'm just going to pop it in my worked example and let you know that it was 0.0707. Look at that, minuscule values. Now before, the uncertainty associated with time was not included in my propagation. This time, however, it does need to be, because time is part of the calculations needed to get my result, my rate of change. So we'll adjust that table too. Now this uncertainty is a big one. The uncertainty was a judgment made in the lab. because the titrations took a bit of time and we were doing them one after another. So if we're thinking that we'd carried them out in the space of about 15 minutes, we thought it was a reasonable estimate to say that the true length of time, between opening the wine and being able to test it might have been out by about 0.25 of an hour. And that's really big for the first test that was carried out after only 1 hour. It's much smaller, proportionately, for the wine left out for several days. Right, so add them all, do your rounding, multiply your total percentage by the rate. Tweak our columns in our data table again, make a new formula for the rate and the uncertainty, etc. In fact, the numbers are so small, you might want to put them into scientific notation or change your units to millimoles. Which means I can multiply everything by a factor of 1,000. Notice if I multiply the rate values by 1,000, the uncertainties automatically adjust. So don't overcorrect. We can do another graph. Pop on error bars in the same way as before. And now the error bars are vastly different because the proportional size of that uncertainty in the units of time. This might go some of the way to explaining why one data point is considerably out of alignment with the others. But it's not everything. At the end of the day, the propagation of uncertainties allows you to comment on the precision of your data and may be a significant source of variance depending on the type of investigation and equipment used. It might also help you identify which part of your experiment contributed the largest uncertainty. When you write an evaluation, you also need to look for the procedural issues or refer back to your qualitative data to find clues that something might have gone wrong. Because actually, maybe that first point was really different to the others because your skill at titration improved over the course of the experiment and your judgment of the endpoint was different. Maybe one of the samples was contaminated, or you had trouble dissolving a solid and there was residue left on the glassware. And challenge your assumptions. Maybe it wasn't just ethanoic acid reacting with the sodium hydroxide. Maybe another acid was present when the wine was first opened, and that got measured. But it was volatile and escaped the flask later on. Who knows? This is where you need to do some research and think about other possibilities. Then you would need to suggest how you might overcome this or what other equipment you could use. At the end of the day, your discussion of equipment uncertainties and experimental errors should help you step back and look at the big picture to make a judgment call about what your data shows and how confidently you can answer your research question.